Hi, in this video we are going to discuss indicators. Imagine a special chemical that behaves like a detective. This detective does not speak, does not fight, it changes color to reveal secrets about liquid by changing its color. This detective is called an indicator. We can say indicator a substance which change their color when pH change from acidic to basic or basic to acidic. And when specific functional group or ions appear or disappear in aqueous solution. These change in color help to find the endpoint of titration. There are different types of the indicator in which one is the acid-base indicators. Acid-base indicators are those substances which are weak acid or weak bases. These substances change their color when aqueous medium changes its pH. In fact, acid-base indicators have two forms and the color of these two forms are different. One exists in acidic medium and other exists in basic medium. So in this way, by their structures or by their colors, these indicators reveal whether the medium is acidic or basic. For example, phenolphthalein is acidic-base indicator. This is a weak acid. In acidic medium, this indicator is colorless and has its unionized form. While on the other hand, when the medium turns from acidic to basic, this indicator ionized and pink color appears. So in this way, by changing structure from unionized to ionized, color change and this tells whether the medium is acidic or basic. We represent this indicator as HPH, which ionize in aqueous medium and form pH negative ion. Note this HPH form exists in basic medium and this is colorless, while on the other hand pH negative exists in acidic medium and show pink color. In acidic medium, H ion is a common ion. It's come from acidic and as well as from this indicator. So according to Le Chatelier principle, this common ion suppress the ionization of this indicator, which is a weak acid or weak electrolyte. And reaction moves backward and form HPH form of this indicator which is colorless. In this way, this indicator in acidic medium shows no color. While on the other hand, when the medium is basic, it means that there are more hydroxyl ions. These hydroxyl ions combine with the proton of this indicator which is a weak acid. In this way, reactions move forward and form more pH negative ions, which show pink color. So this indicator shows color in basic medium at pH 8 to 10. And this indicator is best when we are titrating strong base with weak acid, as this combination forms basic medium at endpoint. For example, we use a strong base, not weak base, like sodium hydroxide, which is a strong base, and add indicator which form pink color. When titrated with known concentration of weak acid such as acetic acid, this acetic acid reacts with sodium hydroxide and forms salt. At the equivalence point, when all the sodium hydroxide used to form salt, the pink color of the solution in Fluorescein becomes colorless. This is endpoint which shows that the medium is no more basic. But in this titration, the sodium acetate is a basic salt, which ionizes and forms basic medium and pH 8 to 10. And again pink color appears. So it is recommended that use indicator with acetic acid in Fluorescein and titrate it with sodium hydroxide. In this way, the endpoint will be very sharp pink color, which is reverse of this titration. This is colorless phenolphthalein. When it's find basic medium or pH 8 to 10, it's give their proton and form anionic species. Here the negative charge involved in resonance or conjugation which opens the ring. Due to this conjugation which happens in basic medium, this shows pink color. In fact, in acidic medium, the gap between pi to pi star is higher. While on the other hand, in basic medium, this gap between highest occupied molecular orbital and lowest unoccupied molecular orbital is lower. This is due to conjugation. And when the gap is lower, this absorbs less energy which is inverse of wavelength. The basic medium this absorb wavelength at about 500 nanometer, which is the wavelength of green color. The complementary color of green is the pink, so pink color appears. While on the other hand, in acetic medium, this form absorb wavelength at about 300 nanometer, which is in ultraviolet region. So this form shows no color. Methyl orange indicator. This is another acid-base indicator. In basic medium, this indicator is unionized and shows yellow color. And in acetic medium, this shows red color and have ionized form. We just represent this indicator as methyl OH, which ionize and form methyl cation and hydroxyline. This unionized form exists in basic medium and shows yellow color, while on the other hand its ionized form exists in acetic medium and shows red color. In basic medium, the hydroxyline is a common ion, and according to Le Chatelier principle, this hydroxyline combined with cation and suppress the ionization of this indicator. So in basic medium, this unionized form of methyl orange exists which shows yellow color. While on the other hand, acid move the reaction forward, and there are more cation which shows the red color. So we can say that acid move the reaction forward and form the ionized form which have red color. And base move the reaction backward and form unionized form which have yellow color. This indicator shows red color when pH is from 3 to 4. This is best when we are titrating strong acid with weak base. This combination establishes the equilibrium at this pH and helps the indicator to show color. For example, when we titrate hydrochloric acid with sodium hydroxide plus indicator which have yellow color. Hydrochloric acid react with sodium hydroxide which is a weak base and form water and salt. This salt is acetic salt which hydrolyze and form hydronium ion which maintain pH from 3 to 4. So at equivalence point when all the ammonium hydroxide used to form the salt, now at the end hydrochloric acid and the acetic salt which dissociate and form hydronium ion maintain the pH from 3 to 4. At this point color change from yellow to red. This is unionized form of methyl orange which exists in basic medium and have yellow color. When this find acetic medium it form coordinate covalent bond with proton. Now this ionized form in acetic medium have nitrogen with 2 methyl group and other nitrogen with positive charge. This increase the conjugation so red color appear in acetic medium. The unionized form of this indicator in basic medium have less conjugation and more gap between pi to pi star. While on the other hand, acetic medium the ionized form have less gap between pi to pi star. Unionized form observe the wavelength at about 450 nanometer, which is the wavelength of violet blue color, which have the complementary color yellow, so yellow color appears. The ionized form observe the wavelength at about 500 to 520 nanometer, which is the wavelength of cyan green color, which have the complementary color red, so red color appears. Litmus is also acid-base indicator. This is a natural indicator which is made from lichen, but this indicator is not being used in acid-base titration. This is because this shows color change at wide range of pH. Blue litmus paper turn red in acetic medium, and when we put that red litmus paper in basic solution, this turns blue. So in this way, this tells about acid-base solution. Redox indicators. These indicators used in redox titration. It tells the exact amount of reducing or oxidizing agents. Redox indicators have two forms. One is the oxidized and other the reduced form. One exists in oxidizing agent and other exists in reducing agent and have different colors. In this way, these indicators tell whether the medium having the oxidizing agent or reducing agent. Such as diphenyl amine is a redox indicator. When it exists in reducing agent, it has reduced form, which shows no color. While on the other hand, when it exists in oxidizing agent, it has oxidized form and show violet color. For example, when we titrate potassium chromate with ferrous sulfate plus indicator. Here, ferrous sulfate is a reducing agent and indicator exists in reduced form which shows no color. When we titrate potassium chromate with ferrous sulfate in acidic medium, this form chromium sulfate, ferric sulfate, potassium sulfate plus water. In this reaction or titration, potassium chromate is oxidizing agent, which is being reduced from +6 oxidation state to +3. While on the other hand, ferrous sulfate is a reducing agent which is being oxidized from +2 oxidation state to +3. At equivalence point, when all the ferrous sulfate is being oxidized by potassium chromate and flask has no further ferrous sulfate, at that point further addition of potassium chromate, which is oxidizing agent, oxidized diphenylamine. And oxidized form of diphenylamine shows violet color, which is the end point. Potassium chromate has its own color, but this not give sharp color at end point, so we use external indicator. While on the other hand, when we use KMnO4 as oxidizing agent, this acts as a self-indicator and then there is no need of external indicator. This is reduced form of diphenylamine in reducing agent which shows no color. And when this find oxidizing agent, it is being oxidized and show violet color. In the presence of ferrous sulfate, this is not being oxidized due to difference of electrode potential. Complexometric indicator. These show different color when they are attached with metal and when they are free. Such as Eriochrome black tea is a complexometric indicator which used in complexometric titration or EDTA titration. This titration helps to find the exact amount of the metal such as calcium, magnesium, etc. For example, when we titrate EDTA with calcium ion plus indicator, this is Eriochrome black tea when it is free and having the blue color. When this attached with calcium ions, its color changed from blue to red. So, Eriochrome black tea, which is a complexometric indicator, have the red color when this is attached with metal and have blue color when this is not attached with metal. When we titrate with ethylene diamine tetraacetic acid, this detach calcium ion from Eriochrome black tea. So at equivalence point, when all the calcium ions are being extracted by ethylene diamine tetraacetic acid, at this point Eriochrome black tea is free and shows blue color, which is end point. Adsorption indicators. These indicators or color substance, when they absorb on precipitates, they show another color. These indicators used in adsorption titration, which help to find out the exact amount of colloid, bromide, and iodide ions. Such as Fluorescein, Acin, these are the adsorption indicators. These both indicators have negative charge. When they absorb on precipitate, show another color. For example, Argentimetric titration. This is a type of adsorption titration in which we use silver nitrate. This helps to find the exact amount of colloid ions, such as when we titrate silver nitrate with sodium chloride solution plus fluorescein indicator. This indicator is negatively charged in the sodium chloride solution and have yellow color. When we titrate silver nitrate with chloride ion, this forms silver chloride. Silver chloride form white precipitations. At equivalence point, when all the chloride ions used to form silver chloride precipitate. After that, there are no chloride ion in the flask. What happened next? When we further add silver nitrate, this gives silver ion which have positive charge. These silver ions, when find no chloride ion, form a layer on silver chloride precipitate. After that, negatively charged indicator fluorescein attach on silver ions. As negatively charged indicator fluorescein absorbed on silver ions, its color change from yellow to pink. This is the end point. This method to find the exact amount of chloride ion is known as Fajans Method. Mohr Method. This method also helps to find out the exact amount of chloride, bromide and iodide ions. But this method not use the adsorption indicator. Mohr method use potassium chromate as an indicator. When all the chloride ions used to form silver chloride, further addition of silver nitrate react with potassium chromate and form silver chromate. And silver chromate shows red color, so this is the end point. Volhard Method. This is also a method which helps to find out the exact amount of the halogen ions such as chloride, bromide or iodide ions. But here again the indicator is not absorption indicator. Volhard method uses ferric indicator such as ferric nitrate. In this method, after equivalence point, when all the chloride ions are used to form silver chloride, we add more silver nitrate. When we add more silver nitrate in flask, this gives free silver ions. At that time, there are no chloride ions. What happens next? We titrate back to find the amount of silver ions in the flask. This time we titrate with potassium thiocyanate. Thiocyanate ions from potassium thiocyanate react with silver ions and form silver thiocyanate. When all the silver ions are used to form silver thiocyanate, further addition of potassium thiocyanate react with ferric indicator. With indicator, this form complex which shows blood red color. This is the end point. Here, potassium thiocyanate tells the exact amount of silver ions. And by subtraction of this amount from total used silver nitrate, we can find the exact amount of the chloride ion. Thanks for watching, and please comment if you have any question.